as a reaction kinetics में था कि what you studied was that it's more about it's basically about the speed or the rate of the reaction, whether the reaction is going to be slow or whether it's going to be fast. So it's the rate of a reaction. Now it depends. In O levels you studied, it's all about collisions of the particles, right? It's if you've got particles, let's say these are particles X, and there are some other particles, they are particles Y. So they're going to react together. They're going to bump into each other, and they would that would lead to collisions. So why do reactions happen in the first place? Reactions happen due to collisions most of the time. They need to collide with each other. When particles collide, when one molecule bumps into another molecule, old bonds are going to get broken, and new bonds are formed. So that's the primary reason why reactions happen. So it all depends on this thing on particles colliding with other particles. So it's all revolving around this. Now, and it's on the collision. It's everything depends. So everything depends on the collisions. Uh, Particles colliding or bumping into each other. Now, these collisions depend on five things. Uh, that is the rate of reaction depending on five things. Number one is temperature. You've got more kinetic energy, that means particles travel faster. So you get more frequent and effective collisions. And also more effective collisions. More effective or successful collisions. So it depends on two things: the frequency, like how much they collide, and effectiveness, like how strongly do they collide. So when you have more kinetic energy, whenever you have more kinetic energy, this is what happens: the particles travel faster, so they're going to bump into each other a lot more. And not only are they going to bump into each other a lot more, they'll also hit each other with a lot more force. Okay? So two things would matter in this case. Just a second. अच्छा ये लिंक किससे मांगा था? Sorry.
Sir, that was me.
ठीक है, just 1 second. So that's rate of reaction, number one. Then now temperature, always, whether it's a solid or a liquid or a gas, it's always going to be a factor. That's the number one factor. Now number two is pressure, but pressure is not a factor always. It's pressure only applies to gases. So it's only a factor for gases because only gases are compressible. So what happens to a container when pressures increase? Its volume decreases. So let's say you have this container and you're trying to decrease. One second. So what you're trying to do is you're trying to decrease the. So here's this piston. Let's say there's this top and it's a movable top and it could move up and down. So you're trying to push it downwards and there are a bunch of gas particles. The blue ones and the red ones. They're all trying to bump into each other. So if you increase pressure, what happens is at higher pressures, volume decreases. So if I compress it and so if I compress it, and this thing starts moving downwards. If it starts moving downwards, all the particles would be a lot closer to each other. So these particles would become a lot closer and you're trying to push it down. So at higher pressure, the volume decreases and particles are closer to each other. Now, because your particles are closer to each other, they would bump into each other a lot more. So you get more frequent collisions. And only more frequent collisions. That's the only thing that's going to change. The effectiveness of collisions remains the same. Why? Because the particles still have the same energy, so they're going to bump into each other with almost the same force. So effectiveness or the successful rate of the collision, it remains the same. TK, is this clear?
Yes, sir.
That's a Baki for number 3. Let's move to number 3. Number 3 is we can talk about surface area. So when it comes to surface area, you've got uh, like if you have powdered or smaller pieces, then instead of one big chunk, smaller pieces have more surface area. So a lot of their particles are more exposed. I mean, they can react. Over here, the middle ones, they cannot react. So if you have more surface area, you're going to get a faster reaction. And why? Because there's going to be more frequent collisions. Over here, the particles that are stuck in the middle, they can't react. Only the surface could react. Over here, the surface, I mean, most of the particles are a lot more exposed. So the surface area is greater. So you get more frequent collisions. So again, the issue is the effectiveness of the collisions kind of remains exactly the same. Number 4 is, let's do concentration. Number 4 is concentration. That is going to affect the rate of the reaction. Always remember, concentration is only an issue, only applies to gases or solutions. Or we can say only applies to solutions or gases. Now, the idea of concentration is it's the number of moles or number of particles divided by unit volume. That's what concentration is, moles over volume. So I have two containers. Uh, there's this container and there's another container which is identical. and both of them have water in them, and there's salt added. So in the first one, there's less salt added. In the second one, there's a lot more salt particles added. So remember the idea of the term concentration. Concentration simply means how far away the particles are or how close together they are. For example, over here, this is higher concentration, obviously. So when something is at higher concentration, the particles are a lot closer to each other. And it's going to be more frequent. And effective collisions. Is this clear?
Yes, sir.
अच्छा फिर fifth अच्छा नहीं frequent effective गलत लिख दिया ठीक है not effective. Uh, the particle is still bumping around with the same energy, so the successful rate or effectiveness of the collisions, it kind of remains the same, except that they bump into each other a lot more because they're closer together. Number fifth, अच्छा fifth है कि that's catalyst. Now what happens when you add a catalyst? Catalyst, what it does is reduces the activation energy. What that basically means is that it becomes easier to break bonds. So now by adding a catalyst, what happens is the frequency of the collisions remains the same. Like for example, if in this beaker I've added a catalyst, the particles are still bumping with each other with almost the same rate. The frequency of the collisions kind of remains the same. So frequency of collisions does not change. Except that they're now more likely to react. So the effectiveness of collisions increases. तो पहले भी 100 collisions हो रही थी अभी भी 100 collisions हो रही हैं except for the fact कि in the first one out of the 100 collisions 5 or 10 of the collisions were successful. Now 50 of them are successful. So the frequency of collisions doesn't change. Effectiveness of collisions increases. So the collisions kind of become more effective because of adding a catalyst. So we're going to first talk about how does a catalyst work. Okay, we all know that it decreases activation energy. That's one. So this is what we're going to start with first. And the first, is पिछला सारा clear? Abdullah, is this clear? Aruba, is this clear?
Yes, sir.
अच्छा, how does the catalyst work? इसमें ना temperature में मैं add कर दूं कि for every 10 degrees centigrade rise, collisions double. The number of collisions double. अच्छा, बाकी है कि how does a catalyst work? The first one is एक सेकंड इसको मैं The first one that we're going to study is heterogeneous catalyst. So this is the type of catalyst where where the catalyst has a different state compared to the reactants. So the catalyst has a different state compared to reactants. Uh, one example is the Haber process. You've got N2 reacting with 3H2 molecules, and it produces 2NH3. So this is a gas. All of them are gases, except that the catalyst has a different state. Iron is a catalyst. Iron is a solid, and it's used as a catalyst. And we're also going to talk about why transition metals are such good catalysts, such good heterogeneous catalysts. So what's going on over here? Why is this reaction speeding up by the addition of iron over here? A couple of things. First, about iron, which are transition metals, and about this reaction. Now, the reaction, one of the reasons why this reaction doesn't happen is it's because of this N2 molecule over here. There's a strong N triple bond, and which is almost impossible to break. So there's this very strong N triple bond N, which is really difficult to actually get rid of or break. N2 is very inert. So how does iron help? Like, I mean, they're going to bump into each other. You'll be increasing temperature. The number of collisions would increase, but no reaction would be happening. So the effectiveness of collisions, I mean, you need both things. You need the particles to bump into each other, but you also need at the same time for them to react with each other. So they would be bumping into each other, but there would be no reaction because it's almost impossible to break the N triple bond N. A very high amount of energy is needed. So that means the activation energy is really high. So this is where the catalyst comes in. So some information about iron, like transition metals are really good catalysts. So at the moment, I'm just going to give you a brief overview why they're good catalysts. Like, you've got potassium over here, which is 19. It has 19 protons. You've got calcium, which is 20 protons. And then when you move forward, you get in the same row you get iron, which is 26 protons. You get copper, which is 29 protons. So these are pretty good catalysts. Reason being, when you move to the right, the protons increase. So you have more protons. So what happens with transition metals like Fe and copper? Transition metals, they don't like to lose electrons because they attract the electrons with a lot more strength. Imagine that iron has 26 protons. Like potassium lost an electron. Why? Because its nucleus wasn't that positively charged. Calcium lost electrons. Why? Because its nucleus wasn't that positively charged. Iron and copper have a lot more protons, so the nucleuses have a lot more positive charge. So they've got more protons. So transition metals, most of the time, they're unreactive. They don't like to lose electrons. But the thing is, they don't have a very strong tendency to actually gain electrons as well. They never form negative ions. Like if you move further to the right, there's going to be bromine with 35 protons. Now bromine would be strongly gaining electrons. It would be forming negative ions because it's got a lot more protons in its nucleus. But these ones in the middle, they kind of don't like to lose electrons. Uh, but they don't also like to gain electrons. Like they hold on to their own electrons very strongly, but they don't have enough protons to gain more electrons or to form a negative ion. Is this point clear?
Yes, sir.
ठीक है सारों को, क्लियर है?
Yeah.
Yes, sir.
Acha. So transition metals are kind of in the mid. They don't like to lose electrons. Instead, they actually have this very slight or weak attraction for electrons. They've got a slight or weak attraction for electrons. And so you have this nitrogen molecule now. And remember, this nitrogen molecule had a strong triple bond. You've got an H2 molecule. Breaking the H2 molecule isn't that difficult. And you've added a catalyst. So there's Fe over here. So here's your Fe catalyst. Now, imagine this N2 molecule and this H2 molecule trying to bump with this. So this molecule is traveling and it's trying to bump with this. This H2 molecule is also bumping with this. What would happen is that the electrons in the triple bond, they would slightly get attracted to the iron. So this is what would start happening in the next step. That if I just copy this, so this is what's going to happen, that the electrons over here in the triple bond and this bond over here, they slowly get attracted to the iron, not that strongly. Similarly, the electrons of H, which they were previously sharing, because of the collision with the iron catalyst, and iron is a transition metal, it has this very weak attraction for electrons. Electrons in the triple bond, they get slightly attracted to iron. Is this point clear?
Yeah.
So now in the process, if the electrons get attracted, where did the triple bond go? It eventually broke. Because all the electrons in the triple bond that were being shared are now being shared between the nitrogen and iron over here. So this step is known as adsorption. This is the first step. So due to what you're going to write is that reactant molecules get adsorbed. It's with a D. And they form weak bonds. Remember, these are very weak bonds. Iron doesn't really like to attract the electrons very strongly. It's a metal. Metals don't like to really gain electrons. If it had been a non-metal, then it would have gained all the electrons. But like transition metals, they don't like to. I mean, they have this weak attraction for electrons, but they don't gain them. So, like platinum is a pretty good catalyst. Platinum really, or gold is a catalyst. Gold really forms ions. So absorbed onto the surface of the catalyst, and they form weak bonds. In the next step, these molecules or these atoms are going to bounce off. So when they bounce off, even the weak bonds over here, they're going to break. So that is known as deadsorption. That the weak bonds between the catalyst and the reactant molecules, they break. And once they break, now new bonds can be formed. So there are two steps involved. Transition metals are good catalysts because, like otherwise, breaking the triple bond was very difficult. But if you added a catalyst, the catalyst would weakly attract the electrons in the triple bond. So the electrons would go missing because they're going to get attracted to iron. I mean, it's not going to happen exactly this way. Like, it's not going to attract all the electrons, but eventually the bond would break. Like, if it's a triple bond, out of the 6 electrons, 4 of them will get attracted to iron. There might be still some electron sharing happening between them, but the bond would be a lot weaker. And the same happens to H2. Like, the bonds or the electrons over here, they will get attracted to the iron catalyst, which is at the bottom. And weak bonds are formed. And in this process, iron is able to sort of break the bonds that were present between the reactant molecules. Is this clear?
Yeah.
Yes.
Okay, so we can kind of just wanted to see if there's a I think as anyways, this is not exactly the right diagram, but probably you can see that some of the bonds would break because the reactants are kind of getting attached to the catalyst. But we can ignore that. Maybe this image is better. So yeah, but you'll get an idea. Anyways, I mean, this is the simplest process, a simplified way of showing this. You don't have to learn any mechanisms, just the general idea of how adsorption and deadsorption is going to happen. And remember, this is always true for heterogeneous catalyst. The other one is called homogeneous catalyst. Now, what happens in homogeneous catalyst is that the reactant and the catalyst, they have exactly the same state. And there is one specific example that you have to do, and that is this reaction. It's Ki reacting with K2S2O8. And it's going to produce, it's going to be Ki, it's going to be 2 Ki. But let me get rid of K. It's 2I minus 1 reacting with S2O8 2 minus. And they end up producing I2 plus SO4 2 minus, 2 of them. That's the reaction that happens. And this reaction has a very high activation energy. Adding Fe2 plus or Fe3 plus catalyst would reduce that activation energy. So these two ions, either one of them, can act as very strong, very good catalyst. So we're going to learn about that in the next class then, okay? ये फिर detail करना. This has to do with electrochemistry. I think we did this in electrochemistry. We'll just quickly repeat it. How does a homogeneous catalyst work, ठीक है? तो next class में फिर continue करते हैं. So, okay everyone.
Okay, sir. Allah Hafiz.
Take care, Allah Hafiz.